Good morning to Dr. Cairo and my fellow friends. I am Chan Wan from Group 1, and today my groupmate and I will be presenting about the topic torsional failure on gas compressor shaft. And here is a brief introduction about my groupmate, Carrie, Catherine, Yongqian, Afnan, and Nazif. Okay, so without further ado, I will be inviting my groupmates to begin the presentation.
Okay, I'm gonna explain to you about definition of torsion. So definition of torsion is the amount of twisting shaft, rod, or bar experienced as one end is forced and the other end is resisting. So for example of the torsion is any motor turning an SL that produce power such as a fan. For definition for torsion natural frequency, torsion natural frequency is at which inertia and stiffness torque are completely in balance.
Hi, I'm Afnan Rozani. I'm going to explain to you about definition of resonance. Okay, definition of resonance is a phenomenon which a vibrating system or external force drive another system to oscillate with greater amplitude at specific frequencies. Definition of design factor. Design factor is defined for an application generally provided in advance and often set by regulatory code or policy, and its actual calculation. The safety factor is ratio of maximum strength to intended load for one item that was designed.
The case study for our project is really about torsional failure in gas compressor shaft, which occurred at the outskirts of Russia, which the compressor experienced a rapid crankshaft failures. The cause of the failure is mainly about torsionally induced alternating stress. As you can see at the picture here, it shows that the end of the compressor experienced a failed surface. Before the failure, cracks appears to be initiated at the end of the keyway close to the flywheel. Having the keywheel causes a greater stress concentration at the product, which is causing the failure to occur.
Today I will talk about, as what Chen says, our failure of compressor gas shaft is the end. Why is the failure occurs? First, the natural frequency. The natural frequency occurs when the shaft is moving. The shaft will experience a frequency. When the frequency achieves a natural frequency, the shaft will experience broke or destroyed. Next is resonance. Resonance will be explained in the next slides. Will be in more details. Okay, here the major resonance is at the big point. The major resonance occurs at the highest frequency. For example, the RPM. The below is the RPM. The RPM at the bottom will be like 55 something, 55. Okay. At the RPM at 55 is the major resonance. The major resonance is where the failures start to occur. Before the 55 RPM and above the 55 RPM, the crankshaft will experience the frequency which is acceptable in the range. Okay, next, dynamic force. What is dynamic force? Dynamic force is the force that experienced by the crankshaft where it results in the extra thrust on the shaft which occurs for the crankshaft to fail. Okay, thank you.
So how does the torsional vibration comes from? The torsional vibration comes from two loads. First is the gas load. The gas load acts on the pistons and is transmitted to the crankshaft in the compressor. The next one is the initial load due to the weight of the piston. By adding these two loads, we can find the combined torsional vibrational load in the system. So, when the system is at resonance, the vibration will occur. As the speed increases, the speed of the system will increase until it reaches a maximum revolution per minute (RPM) at its natural frequency, at its torsional natural frequency. Therefore, torsional analysis is very important in predicting the resonance conditions and vibration conditions. These are the following consequences if the system fails. First is the broken crankshaft, and the second one is the destroyed couplings, and the third one is the broken engines.
Okay, next I will be explaining the solution, which can be set as some suggestions to improve the system. Okay, first is to order a torsional vibrations analysis before the system is built. This is to ensure that the torsional vibration can be accepted. Okay, next is the system can be modified to a more cost-effective system. Therefore, the system can be last longer and also would undergo failure easily. The next is changing the coupling size or style. The system, the most ideal system for the compressor is in the cylindrical shape. Okay.
There are several reasons why we need to perform torsional analysis. First is to improve the design methodology to prevent future catastrophic failure. And second is to allow the end user to perform a baseline startup checks instead of waiting expensive failure to occur. Third is to avoid destructive failure, and of course to lower the maintenance costs. Last but not least is to improve the productivity of the product and maintain the quality. That is all for our presentation. Thank you.
In this module, we will discuss torsional vibration. This topic builds on many terms introduced in Module 1, namely natural frequency, resonance, and dynamic forces. All rotating equipment, including compressors, engines, and pumps, will experience a torsional load. One important torsional load is the gas load inside a reciprocating compressor. The gas load acts on the piston and is transmitted to the crankshaft. This chart illustrates the gas load from all the cylinders during one revolution of the crankshaft. Another important load is the inertial load due to the weight of the piston assembly. Inertial load for all cylinders also varies widely over each revolution. By adding together the gas load and the inertial load, we find the combined torsional load for all cylinders in this compressor. The load from each cylinder acts on the crankshaft, resulting in a torque that can cause vibration problems. Each machine will have a unique load profile. A torsional vibration analysis considers how this combined load interacts with the crankshaft, the engine or motor, the coupling, and the resulting stress and vibration on the system. A complete drivetrain or torsional system, for example, a reciprocating compressor with a coupling and an electric motor, has a torsional natural frequency, or TNF. Torsional natural frequency is defined as the frequency at which a shaft twists back and forth. Imagine twisting a shaft by rotating one end. After releasing the shaft, it rotates back and forth. This oscillation occurs at the torsional natural frequency. This is analogous to the mechanical natural frequency described in Module 1. Torsional vibration can occur, especially if the system is resonant. In this example, the vibrations are low at 900 RPM. As the speed increases, the system becomes resonant at 1200 RPM when the speed is at the TNF. At resonance, the vibration response is greatly amplified. Above the resonant frequency, vibration response is significantly reduced. The torsional analysis must accurately predict resonant conditions and vibration problems. If not, the results can be catastrophic. Destroyed couplings, broken compressor shafts, broken motor shafts, not to mention the downtime and cost if the unit is inoperable for 1 to 2 months. Torsional vibration is often called the silent killer because a failure like this occurs without warning. The best way to mitigate these failures is to order a torsional vibration analysis before a unit is built. With early involvement, the system can be modified more cost-effectively and easily than later. Changing the coupling size or style, adding a flywheel, or a detuner, and changing the shaft material or size are all easily done if the components haven't been built. If the system is already built, then needed modifications are often more expensive and complicated, resulting in delayed delivery of the unit. The next time you are involved with ordering or designing a rotating system, it is highly recommended that you have a torsional analysis performed. This module is a brief introduction on torsional vibration analysis. The key points are that torsional vibration can result in failure. A torsional vibration analysis should be performed very early in the package design phase. The analysis should adequately cover the entire operating condition envelope, including upset conditions, while addressing tolerances in manufacturing and installation. For superior accuracy and practical recommendations, please contact Beta for your next compressor or pump project.